Okay, this continues section 3.5. We were just talking about the additive properties with the slopes, and we were seeing that we could add whatever the independent change was to our independent values and the dependent change to our dependent values and get from one point to another. Or we could work backwards in that too. And we don't want to forget that we can also give an equation of a line based upon the slope or the rate of change and the y-intercept. You're going to hear me talk a little bit more about this as the rate of change and the baseline. And then another thing we might want to do is to see if ordered pairs or if a function represents a linear equation. And the thing that we need to realize about a linear equation is that a model is linear if the rate of change is constant for any values of x and y. And we're going to see that consistent rate of change from one value of the x's to one value, the next value of the x's to the next value of the x's as being constant, from the one y to the next y to the next y being constant. So let's take a look at an example where we're trying to decide if we have a linear equation or not. So looking at these two tables of values, we can see if these are linear by seeing the changes in the x's and the changes in the y's. So on part A, what we see is that the x's change from the first ordered pair to the second is a 4, and from the second ordered pair to the third ordered pair is another 4, and it's a positive 4. We're increasing on those. And then looking at the y's, what we see is the y's go from a -5 to a -1 to a -5, which is in a decrease of 4. And then from the second to the third ordered pair, we see only a difference of a -3 this time. And so what we are seeing is not constant rate of change here. And because this is not constant, that means that this function or this equation is not a linear equation or not a linear function or a linear model. So this one's not linear. Now in part B, let's investigate the same thing. So from the first ordered pair to the second ordered pair, let's look at the x's, how they change. The x's go from -4 to +4. -4 to +4, that's a change of 8. And then from the second ordered pair to the third ordered pair, we go from 4 to 12. That's another change of 8. Now let's go investigate the y's. And the y's go from 2 to -4. So that's decreasing, and that's decreasing by 6. And then from -4 to -6, that's also decreasing. So that's decreasing again by -6. And so these are constant and these are constant, so this looks to be linear. And the reason that it looks to be linear, of course, is because we have constant rate of change as a ratio of y's change to x's change. And you see that if you take two of these at a time, this one and this one, and this one and this one, what we're seeing there is slope, right? It's -6 over 8, -6 over 8. And for slope, of course, we reduce that down to a simplified version of the ratio. But that is what we're looking for to be a linear equation or not. Okay, now next we're going to do an example where we're going to use our slope-intercept form written as the dependent value is equal to the baseline plus a rate of change times the independent value. And we can use units to help us out in that. So join me for the next video and we'll talk about an example where we're doing an application.